So that is the general pattern of evolution for stars with mass over 8 solar masses. We've had that down. Before we finish the dramatic end, we need to make some comments on stars that are actually really big. Masses over, say, 20 solar masses. These are the O-type stars. They are rare, but their evolution is interesting. First distinction we notice is that when these guys depart the main sequence, they do not brighten. There's no red giant phase. They're already giants. They do redden, but they don't increase their luminosity so much. What's going on is there's no core collapse going on. The helium core does not collapse. Temperatures and pressures are high enough in the core of these huge stars for helium fusion to begin without core collapse. So there's no red giantism phase, such as it is. They're red supergiants, but that's because they were already large. The other thing that happens in these large stars is that the growth of the envelope as the star cools, even maintaining its luminosity, they become huge, the envelope is poorly bound, and rates of mass loss become humongous. They lose as much as a 10,000th of a solar mass per year. This is an amazing amount of stellar wind coming off at high velocities. What the spectral signature of this is that their spectrum is dominated by not absorption lines in the atmosphere, but emission lines in the atmosphere at this point in their evolution. We get a spectrum that's dominated by the emission lines with a characteristic so-called P Cygni signature of mass loss. We won't play with the line shape for lack of time. And in addition, in general, O-type stars show evidence that they rotate more rapidly than other stars. And a very recent result, which may be pertinent to understanding how all this comes about, is that over 3/4 of O-type stars are in binary systems. Remember this to be compared with somewhere between about a third or a fifth of the general star population is in a binary system, and about half of them have partners close enough to have undergone mass transfer, as we discussed in the past. What this tells us is perhaps that O-stars are rare. It's difficult to make an O-star. Perhaps the only reason we find so many of them is that many of them were not initially O-stars, and certainly this will affect the way they evolve. The research on that is definitely still ongoing. But these high mass loss stars, the technical term is Wolf-Rayet stars for the people who classified them, and these are these stars with these large emission lines in their spectrum, and the nature of the emission lines is as well interesting. We find typically very little hydrogen emission. We find classification by the spectrum, WN stars are dominated by nitrogen emission lines, WC stars by carbon emission lines, and the rare WO stars by oxygen emission lines. And the understanding of the mechanism is that essentially these Wolf-Rayet stars have already lost their hydrogen and helium envelope, and what we're seeing is a stellar wind essentially composed of the dredged up interiors of the stars, and these stars losing huge quantities of heavier fusion products into the interstellar medium are very important for producing the seeding of the interstellar medium with these heavy elements. And this phase of evolution, it is typically thought, is followed by core collapse supernova. We'll talk about what happens when the core collapses in a bit. But many of these stars do not survive to an actual horizontal branch. They go off into Wolf-Rayet and lose their envelope, and at this point the core collapses. Though, as we will see, where this is not completely true, we have evidence that some of them do manage a return to blue supergiant status. In stars that are even more massive, with masses above, say, 50 solar masses, these don't even make it to the red side of the spectrum. They never even red significantly. These stars are very poorly understood. The most famous and, in some sense, enigmatic of the class is Eta Carinae. This is a star that famously in 1837, for a long, extended period of time, brightened to immense luminosity. You can see 20 million solar luminosities compared to its current quiescent mere 5 million solar luminosities. So this is a monster of a star. This is a recent Hubble Space Telescope image showing dramatic evidence of the mass loss. You see the polar flow of the ejecta, as well as some kind of strange fragmentary disk structure that's not well understood. These, as they're called, luminous blue variables, are very poorly understood stars, but again, they clearly play a critical role because of the large amounts of heavy elements that they emit in driving the structure of the interstellar medium, and as we shall see when we talk about galaxy structure, in driving the dynamics of star formation in the galaxy.